It was moving too fast to be natural. Astronomers watched the point of light cross their screens and knew almost immediately that something was wrong with it. Not wrong in the sense of a glitch. Wrong in the sense that it did not behave like anything they had ever tracked before. It had no tail, no glow, no halo of gas boiling off its surface the way a comet's should. It simply moved. Fast. And getting faster in a way gravity alone couldn't explain. For a few days in October 2017, a single object put the entire field of astronomy on alert, because for the first time in recorded history, something had entered our solar system from somewhere else entirely, and nobody could agree on what it actually was. This is the real story of Oumuamua. The discovery happened on October 19, 2017, at the Pan-STARRS 1 telescope on the summit of Haleakala, Maui, operated by the University of Hawaii's Institute for Astronomy. The telescope was built for exactly this kind of job, scanning the sky night after night, hunting for anything that moves against the fixed backdrop of stars, anything that might be a hazard, an asteroid, a comet, a piece of the solar system nobody had catalogued yet. Astronomer Robert Warwick was the one who noticed it, a faint smear of light drifting across multiple exposures, moving in a way that didn't fit any known orbit in the solar system's catalog. He checked the archive. He found it again in images from the night before, a fainter, easy-to-miss streak that had gone unnoticed at first pass. 2 nights of data, 1 trajectory. And that trajectory made no sense for anything born in our solar system. Every asteroid, every comet, every icy fragment that has ever been tracked in the solar system shares one thing in common, a bound orbit. They loop around the sun. Ellipses, some stretched thin, some nearly circular, but always closed curves, always gravitationally tied to our star, always born here in the disk of gas and dust that became the planet's 4.5 billion years ago. This object's path was not an ellipse. It was a hyperbola, the shape of a trajectory for something that arrives once, swings past the sun, and leaves forever. It was moving too fast for the sun's gravity to ever pull it back. It came from outside, and it was already leaving. Within days, astronomers around the world redirected their instruments toward it, racing to gather as much data as they could before it vanished back into the dark between the stars. The European Southern Observatory's Very Large Telescope in Chile, the William Herschel Telescope in the Canary Islands. Observatories on nearly every continent turned their optics toward a single point of light, because everyone understood what they were looking at. The numbers, once astronomers worked them out, were almost impossible to process. It had traveled for hundreds of millions of years, possibly longer, drifting through interstellar space before it ever crossed into our solar system. Its closest approach to Earth had already happened, on September 16, 2017, a month before anyone even spotted it, at a distance of about 24 million kilometers, roughly 60 times farther than the Moon. Close, in cosmic terms. Close enough that if it had been discovered even a little earlier, or if its geometry had been slightly different, the story might have unfolded very differently. It had passed even closer to the Sun on September 9th, swinging inside the orbit of Mercury at just over 38 million kilometers, whipping around our star at a velocity of nearly 88 kilometers per second before beginning its outward journey, the very maneuver that let astronomers calculate, beyond doubt, that this thing was not gravitationally bound to us. By the time Pan-STARRS caught it, the object was already outbound, already leaving, already a temporary visitor with an expiration date measured in weeks. That urgency reshaped everything. Astronomers were not studying a permanent resident of the solar system. They were racing a closing window, trying to extract every possible detail from an object that would soon be too faint, too distant, and then simply gone. The only interstellar visitor humanity had ever directly observed, vanishing back into the galaxy before most of the public even learned it existed. The naming alone tells you how seriously this was taken. The International Astronomical Union designated it 1I 2017 U1, that leading 1I marking it as the first interstellar object ever catalogued, a new class of object requiring an entirely new label. The Pan-STARRS team, working with Hawaiian language experts, gave it the name Oumuamua, roughly translating to a messenger from afar arriving first, or scout. A name chosen because that's exactly what it was believed to be, the first of its kind ever seen, possibly not the last. Then the real strangeness began. As more telescopes gathered light from the object, astronomers tried to do something ordinary, measure its brightness as it rotated to estimate its shape. Most asteroids vary somewhat in brightness as they tumble, because they're irregular lumps of rock, brighter when a wider face catches the sunlight, dimmer when a narrower edge turns toward us. Oumuamua's brightness didn't vary somewhat. It varied by a factor of 10. A factor of 10 is not subtle. A factor of 10 means the object's silhouette had to be extraordinarily elongated, dramatically longer than it was wide, spinning end over end with a period of roughly 8 hours. alternately presenting a broad face and what was essentially an edge-on sliver to any telescope watching from Earth. Models built from that light curve suggested a length-to-width ratio possibly exceeding 6:1, and by some estimates even more extreme, a shape unlike any asteroid or comet ever measured in our own solar system, where objects tend toward roughly potato-shaped or spherical, not needle-thin or disc-flat. Estimates for its size settled around 100 to 400 meters in its longest dimension, though the uncertainty was significant because astronomers were reconstructing a three-dimensional shape from nothing but a flickering point of light 30 million kilometers away. No image existed, not one. Oumuamua was too small, too distant, and moving too fast for any telescope on Earth to resolve it as anything more than a single unresolved point. Everything scientists learned about its shape came from indirect inference: light curves, color data, spectroscopy, never a photograph. To this day, no one has ever seen what Oumuamua actually looked like. Every artist's rendering of a cigar-shaped or pancake-shaped rock drifting through space is exactly that, an artist's rendering, an informed guess dressed up as an image. Stay with me, because the color data made things stranger still. When astronomers ran spectroscopic analysis on the faint light reflecting off Oumuamua's surface, they found something that didn't match any single category of object previously studied. Its color shifted depending on which part of its light curve was being measured: reddish, consistent with a surface that had spent eons bombarded by cosmic rays, the kind of space weathering seen on comets and certain asteroids in the outer solar system. But not uniformly reddish. In places, the spectrum came back closer to neutral, more like an S-type asteroid than a comet. That inconsistency mattered. A single uniform body should weather uniformly, presenting a broadly consistent surface signature regardless of which face happens to be turned toward the sun. Oumuamua's shifting color suggested either a surface with patchy, uneven composition, or an object tumbling chaotically enough that different, structurally distinct sides were being exposed to Earth's telescopes at different points in its rotation. No rotational axis could be reliably pinned down either. Most tumbling bodies eventually settle into a stable, predictable spin. Oumuamua's rotation looked excited, chaotic, non-principal axis tumbling, the kind of motion you'd expect from an object that had been struck, fractured, or violently ejected from its parent system relatively recently, at least on cosmic timescales, and hadn't yet had enough time for its spin to settle into equilibrium. Every new measurement seemed to rule something out without ever fully ruling something in. The Spitzer Space Telescope observations deserve particular attention because they represent one of the most rigorous attempts to pin down Oumuamua's physical properties before it slipped permanently out of reach. Spitzer, operating in infrared wavelengths invisible to ground-based optical telescopes, was uniquely positioned to detect the faint thermal glow of dust particles that cometary activity would produce, even dust too faint for any visible light instrument to catch. Researchers pointed Spitzer at Oumuamua's last known position and searched exhaustively for any trace of carbon dioxide, carbon monoxide, or dust emission. They found none, setting some of the tightest upper limits ever placed on activity from a body of that size. The non-detection wasn't a failure of the instrument. Spitzer was sensitive enough to have caught even weak outgassing if it had been occurring at the level required to explain the anomalous acceleration through conventional cometary mechanics. Its silence was, in its own way, a measurement, powerful evidence that whatever process was pushing Oumuamua away from a purely gravitational path, it wasn't behaving like any comet ever previously studied. That single null result did more to fuel the ongoing debate than almost any positive detection could have. It ruled out the simplest explanation without offering a replacement, leaving exactly the kind of vacuum that competing theories, from Loeb's light sail to the eventual nitrogen ice model, rushed to fill. Then came the detail that turned a strange discovery into an outright mystery. As Oumuamua left the solar system, astronomers tracked its trajectory with the same precision used for spacecraft and near-Earth asteroids, refining the orbit again and again as new observations came in. And the object wasn't following the path gravity alone predicted. It was accelerating. Ever so slightly but measurably, pushing away from a purely gravitational trajectory as it departed. For a comet, this would be unremarkable. Comets do this constantly. As sunlight warms their icy surface, gas sublimates and jets outward, and that outgassing acts like a tiny rocket thruster, nudging the comet's path away from a pure gravitational curve. Astronomers see this all the time. It's expected. It's boring, even. Except Oumuamua showed none of the signatures that should come with outgassing. No coma, the diffuse cloud of gas and dust that surrounds an active comet's nucleus. No detectable dust trail, no spectroscopic evidence of gas being released. Multiple deep observations, including from the Spitzer Space Telescope, searched specifically for the carbon-based molecules and dust that cometary outgassing produces. They found essentially nothing. an object accelerating like a comet, behaving in every visible way like bare rock. That contradiction sat at the center of the entire scientific debate that followed, and it's the reason Oumuamua refused to fade quietly into an academic footnote the way most minor discoveries do. Anomaly 1. An object with no cometary activity, behaving exactly as though it had cometary activity. Anomaly 2, a shape so extreme that nothing in the solar system's own asteroid or comet population comes close to matching it. Anomaly 3, a chaotic, unsettled tumble suggesting a relatively recent violent event in its history, despite an inferred age that likely predates the solar system itself. Anomaly 4, a trajectory so precisely hyperbolic that its interstellar origin was never in serious doubt, arriving from the general direction of the constellation Lyra at a speed too great for anything short of an origin beyond our star's gravitational reach. Individually, each anomaly had a plausible, if incomplete, natural explanation. Together, stacked one on top of another, they created exactly the kind of ambiguity that makes for genuine scientific controversy rather than a quickly settled question. When researchers looked again at the combined data set, running increasingly sophisticated models trying to reconcile every anomaly simultaneously, no single natural scenario emerged as a clean, universally accepted fit. Each explanation solved some of the puzzle while leaving another piece unaccounted for. That's the environment Avi Loeb's proposal landed in, not a settled scientific consensus he was recklessly challenging, but a genuine, unresolved gap in the data that conventional models were struggling to fully close. Then, in November 2018, the story took its most controversial turn. Avi Loeb, chair of Harvard's astronomy department at the time, co-authored a paper with postdoctoral researcher Shmuel Bayali, proposing an idea that made headlines around the world, that the unexplained acceleration might be evidence of a thin, artificial structure, a light sail, something built, not grown, something that could be pushed by the pressure of sunlight itself, explaining the extra thrust without any need for gas or dust that observations had failed to detect. Loeb didn't stop at that one paper. He continued to argue, publicly and repeatedly, that Oumuamua's extreme shape, its lack of any cometary activity, and its anomalous acceleration collectively pointed towards something beyond a natural explanation, possibly technological debris, a discarded fragment of alien engineering drifting between the stars long before it ever crossed our path. He later expanded the argument into a best-selling book, turning what had been a niche astrophysics debate into a mainstream conversation about whether humanity had, for a few brief weeks, been in the presence of something built by another civilization. It was a bold claim from someone with genuine scientific standing. Loeb held one of the most prestigious chairs in American astronomy, and his willingness to entertain the artificial origin hypothesis in a peer-reviewed publication, rather than confining it to speculative commentary, forced the rest of the field to engage with an idea most astronomers would otherwise have dismissed without a second look. He didn't stop there. In the years that followed, Loeb went on to found the Galileo Project at Harvard, an initiative explicitly built to search for physical evidence of extraterrestrial technology, from interstellar objects like Oumuamua to unexplained aerial phenomena closer to home, using rigorous instrument-based methodology rather than anecdote. To Loeb, Oumuamua wasn't just an anomaly to be explained away. It was a case study in what happens when the scientific community encounters something it cannot immediately categorize, and reaches for the most conservative explanation available almost reflexively, simply because the alternative is uncomfortable. That argument, that scientific caution can shade into scientific bias, became almost as controversial as the light sail hypothesis itself. And it was met almost immediately with equally forceful pushback from much of the astronomical community. The counter-argument didn't take long to arrive, and it came from multiple directions at once. Most planetary scientists pointed out that unusual does not mean artificial, that Oumuamua being the first interstellar object ever observed meant, almost by definition, that it would look like nothing we'd catalogued before, simply because we had never had a comparison sample. A sample size of 1 tells you almost nothing about what's typical for objects from other star systems. It only tells you that this particular object was strange, not that strangeness requires an artificial origin. More importantly, natural explanations began to emerge that could account for the puzzle without invoking anything built by intelligent hands. In 2021, a research team led by Daryl Seligman and Stephen Desch proposed that Oumuamua might be composed largely of solid nitrogen ice, the same material that forms the frozen surface of Pluto and Neptune's moon Triton, a fragment potentially chipped off the surface of a Pluto-like exoplanet during some ancient, violent collision in another star system, then flung outward by gravitational forces to drift alone for hundreds of millions of years. Nitrogen ice, the researchers argued, sublimates at extremely low temperatures and could produce enough outward thrust to explain the acceleration, while releasing so little detectable gas that instruments on Earth might simply not have been sensitive enough to catch it. The extreme flattened shape in this model wasn't an artificial hull. It was the natural result of a nitrogen iceberg slowly eroding as it warmed near the sun, thinning unevenly the way a bar of soap wears down under running water, shrinking, flattening, losing mass unevenly until it became the pancake-shaped sliver astronomers measured. Other teams proposed alternative but similarly natural mechanisms, that Oumuamua could be an unusually porous, low-density dust bunny aggregate, fragile and fluffy enough that outgassing from deep within its structure could occur without producing the dust signatures a denser comet would leave behind. Still others modeled it as a fragment shed from a larger interstellar body during a tidal disruption event, torn apart by gravitational stress, the way Earth's own moon-forming impact once reshaped raw material into new configurations. None of these explanations required anything beyond known physics and known chemistry. Each attempted to account for the same handful of anomalies: the shape, the lack of visible outgassing, the anomalous acceleration, using processes astronomers already understood from studying our own solar system's icy bodies. The nitrogen ice model in particular gained traction because it made a testable prediction rather than simply patching over the anomaly. If Oumuamua really was a fragment of nitrogen ice chipped from the crust of a Pluto-like world, then similar fragments should statistically be relatively common throughout the galaxy. Every planetary system that forms a Pluto-like body at its outer edge, then experiences the kind of violent collisional history our own Kuiper belt shows evidence of, should be capable of producing and ejecting nitrogen ice debris on a regular basis. That prediction gave researchers something concrete to search for in future interstellar detections, rather than leaving the explanation as an untestable one-off. Critics of the nitrogen ice hypothesis raised their own objections. Some pointed out that nitrogen ice is fragile, and that a body composed largely of it should not have survived hundreds of millions of years of cosmic ray bombardment and interstellar travel without disintegrating long before ever reaching our solar system. Others questioned whether the specific thrust profile calculated from Oumuamua's trajectory data actually matched what a nitrogen outgassing model would predict, or whether the fit was closer than the uncertainty in the original data really allowed. The debate never fully resolved. It couldn't. Oumuamua was already gone by the time most of these papers were published, hurtling back into interstellar space at tens of kilometers per second, too faint for any existing telescope to observe in further detail, its true composition and shape locked away in data that will likely never be supplemented by so much as a single new observation. What remained was a scientific standoff. On one side, a minority position, championed loudest by Loeb, arguing that the artificial hypothesis, however extraordinary, could not be ruled out by the data, and that dismissing it outright reflected discomfort with the implications more than a rigorous weighing of evidence. On the other side, the mainstream consensus, backed by an increasing number of published natural models, arguing that unusual physics, however unfamiliar, offered a more parsimonious explanation than invoking an alien civilization on the strength of a single, ambiguous data set. Both sides agreed on one thing at least. Oumuamua mattered, not because it settled anything, but because it was the first proof that objects from other star systems can and do pass through our own, close enough to observe, close enough to measure, close enough to remind an entire planet that the solar system is not a sealed room. The scale of what that means is difficult to sit with for long. If a single interstellar wanderer drifted through a region as small, cosmically speaking, as the inner solar system, and happened to pass close enough for a ground-based telescope to catch it during a brief and specific window of visibility, then similar objects have almost certainly been passing through for as long as the solar system has existed, unnoticed, unrecorded, invisible to instruments that, until 2017, had never been sensitive enough or systematic enough to catch one. Estimates published in the years following Oumuamua's discovery suggested that interstellar objects of similar size might pass through the inner solar system far more frequently than anyone had previously assumed. Some models proposing several such objects could be present within the orbit of Neptune at any given time, simply too small and too faint for existing surveys to detect them. That estimate alone reframes the entire discovery. Oumuamua wasn't a freak, one-in-a-billion-years event. It may have been the first one we were simply capable of seeing. Which is why, less than 2 years after Oumuamua vanished, a second interstellar object confirmed that the first sighting was not a fluke. In August 2019, amateur astronomer Gennady Borisov, observing from Crimea with a telescope he built himself, discovered a second object on a clearly hyperbolic trajectory, 2I Borisov, the first interstellar comet ever confirmed. Unlike Oumuamua, Borisov behaved exactly the way a comet should. An obvious coma, a visible dust tail, active outgassing consistent with a normal icy nucleus. It offered no mystery, no artificial hypothesis controversy, no extreme unexplained acceleration. In a strange way, that made it the perfect counterpoint. Borisov proved that interstellar objects were real, that they do pass through, and that most of them, unlike Oumuamua, look and behave exactly as expected. It made Oumuamua's strangeness stand out even more sharply by comparison, a genuine outlier even within a newly discovered category of object.